Good morning, guys. Today is our last day to talk relativity, so I'm hoping I could bring it all into focus for you. I know that for many of you this was a topic that didn't seem to make sense. Well, that's because it doesn't make sense. Relativity only kicks in, at least in terms of noticing it, at very high speeds. So these are all things that we would not have noticed at normal everyday speeds. Even though they do happen, the effects are really small. So we have Einstein's special theory. Again, special theory means this only applies if you're not accelerating. One invariant, speed of light. This is important. Every observer in the universe sees the same speed of light, regardless of what frame of reference they're in, regardless of what light source they are looking at. No matter what light you see, it will always be traveling at the same speed. It is the only thing that stays constant in the universe. Okay, the effects of this. Effect number one, time slows down for frames of reference that are in motion relative to you. A person on this ship will have their time passing more slowly than the person who is viewing them from Earth. This can be significant. If this ship is traveling fast enough, the person on the ship will not seem to be aging when viewed from Earth. That ship could travel for hundreds and hundreds of years, and when it returns back to Earth, the person on that ship will not have aged anywhere near as much as the person who stayed behind on Earth. Time slows down. This is not just some theoretical thing. This is something we have been able to prove. I want to mention it again. We see this actually happening with atoms, with their half-life. We see it happening with super accurate clocks. We can measure this effect at really low speeds. And we absolutely, positively have to take this into account with GPS satellites. Even at slow speeds like 7,000 meters per second, this effect is enough that it would screw up our navigation had Einstein not discovered it. I want you guys to realize your biological clock also would slow down. Your aging process would slow down. All things that depend on time would slow down in that moving frame of reference. When this person is viewing this frame moving relative to them, everything slows down in the exact same proportion. Remember that when you hit the speed of light, when we see that ship traveling at light speed, time doesn't just slow down, it stops. It literally stops. If I dropped my iPad, it wouldn't fall. I wouldn't know it didn't fall because the processing in my brain would stop too. All things that have time involved with them would stop at the speed of light. It would seem as though time itself stopped. Consequence number two is that distances are no longer the same for all frames of reference. So this person in the ship would see the distance between these two planets as much shorter than the person who is on Earth. Conversely, this person on Earth would see the distance of this ship, the length of the ship, the size of the ship contract. And if that ship was traveling fast enough, it would contract so much as to disappear. The length would go to zero at the speed of light. The third and final consequence is so fundamentally important, and that is mass is also different. So a person on Earth viewing this elephant and a person in the ship viewing that elephant would see the elephant with a different mass. The person in the ship is not seeing the elephant move, so they measure the real mass. The person on Earth is seeing the elephant in motion, so they would see not a smaller mass, but a larger mass. Mass gets larger when the object is in motion relative to you. it turns out that mass goes not to zero, but to infinity. So as that ship got closer and closer and closer to the speed of light, the mass of that elephant would approach infinity, meaning the elephant alone would weigh more than the entire universe. This is a reason why we will never be able to get an object to the speed of light. The object would take on a mass bigger than the universe. Trying to accelerate that object would require a force that was infinitely large. We have our Newton's law that still applies. Acceleration equals force over mass. If you have an infinite mass, you're going to have no acceleration. So at the speed of light, you cannot go any faster. Okay, it's the cosmic speed limit. It is the fastest speed we can ever achieve. And at that moment, the mass of the object would be the mass of the entire universe and then some. Okay, the final consequence I had you guys try to figure out on your own. Unfortunately, only 2 people in all the classes were able to figure this thing out without help from me. And this is a really important result. So let's take a look at this consequence 4. This is where you want to make sure you start adding this into your notes. We haven't talked about the result yet. Kinetic energy of the ship. How is the kinetic energy of the ship going to change as the ship moves faster? Remember, kinetic energy is a relative term. The guy on the ship doesn't know the ship is moving because relative to him it's not. And that's a valid way of looking at things. The guy on the ship sees no kinetic energy. But the guy on Earth does see this ship moving. It is moving relative to him. He does see it with some kinetic energy. And when we plot out a graph of the kinetic energy, not with some fancy equation, but you just simply use kinetic energy equaled 1/2 mv squared. Okay? You just plotted that out using the old kinetic energy formula. And then if you compare that kinetic energy to the change in mass that takes place based on special relativity, it turns out that you get a proportional graph. If there's no change in mass, there's no kinetic energy. The greater the change in mass due to your motion, the greater the kinetic energy. Okay, so what? It's proportional. Here's where it becomes important. You look at the slope. You think about the equation. Kinetic energy equals 9e to the 16th, and almost all of you got that right value for the slope, times x, which is delta m. So we have y equals mx, our normal equation for a linear graph. The slope is this 9e to the 16th. What is 9e to the 16th? Why is that an important number? Well, it turns out that that is 3e to the 8th squared. 3 to the 8th, that's the speed of light. So this slope, for some reason, is the speed of light squared. And now if we look at our equation, we have energy, kinetic energy in this case, is equal to the speed of light squared times the change in mass. And lo and behold, we got one of the most important physics equations ever, just from working through a real simple graph. We've got the energy that we've given to our ship is equal to the change in mass times the speed of light squared. E equals mc squared. The energy we gained came from a change in mass. Okay? So I want you guys to realize when we talk kinetic energy, what we're saying is that kinetic energy is a result of the change in mass. We've given the object kinetic energy. It manifests itself in a change in mass. As that ship is whipping by us, that kinetic energy that we so-called kinetic energy that we talk about is a result of the fact that we see this ship with more mass than the person on the ship. E equals mc squared. Okay, and that's where I would like to end our study of relativity. 4 big consequences. Time slows down. Length gets shorter. Mass gets larger. And kinetic energy is a result of a change in mass.